In this video, we're going to talk about important properties of logarithmic functions that can be used to simplify logarithmic expressions and solve equations that involve logarithmic terms. Recall that the logarithm with base a is just the inverse of the exponential function with base a. And shown here, just to remind you, is a logarithmic curve whose base a is greater than 1. As we're about to see, just as exponential functions enjoy various properties that make computations involving exponential terms easier, logarithms enjoy various properties that make computations involving logarithmic terms easier. And those properties are arrived at simply by undoing familiar rules of exponents. One of those properties of exponents has to do with powers. To be more precise, if you take an exponential term, a to the x, and raise it to some power n, then we know that we can take that power and multiply it by the exponent x. That is to say, a to the x raised to the power n can be rewritten as a to the n times x. The exponents simply multiply together here. Another property of exponents has to do with products. A product of two exponential terms over the same base, a, can be rewritten as shown. A to the power x times a to the power y is equal to a to the power x plus y. Here the exponents add together. There's also this property involving quotients, aka one thing divided by another. One exponential term a to the x divided by another exponential term a to the y with the same base can be rewritten as a to the power x minus y. Here the exponents get subtracted. As we'll see, each of these three rules has a counterpart for logarithms, which makes sense because logarithms are, after all, merely the inverses of exponential functions. Here's our first property of logarithms. It's often called the power rule of logarithms. And what it states is that the logarithm of a power, the logarithm of x raised to the power n, can be rewritten by taking that power and moving it out to the front of the logarithm. So the logarithm of x to the power n is equal to n times the logarithm of x. And to check your understanding, let's think about a quick example. See if you can use the power rule of logarithms to rewrite the expression logarithm with base 10 of radical x. The thing to notice here is that the logarithm of radical x can be rewritten as the logarithm with base 10 of x raised to the power 1/2. And as soon as we realize that, we can use the power rule to take that exponent of 1/2 and write it in front of the logarithm, giving us 1/2 of the logarithm of x with base 10. Our next property is often called the product rule of logarithms, and it states that the logarithm of a product of two things, the logarithm of x times y, can be rewritten as a sum of logarithms, the logarithm of x plus the logarithm of y. As you can probably guess, this rule simply comes from reverse engineering the product rule for exponential terms. Once again, let's check our understanding of this rule by considering a simple example. See if you can use the product rule to expand the expression natural log of 2x. Here it's quite straightforward. The natural log, which is just the logarithm with base e, of 2x can, by the power rule, be rewritten as the natural log of 2 plus the natural log of x. Or, if we want to do it the other way around, the natural log of x plus the natural log of 2. And this little example shows us something rather interesting about logarithms. It shows that multiplying the input of a logarithm by a constant is actually equivalent to adding a constant to the output of the logarithm. Finally, let's have a look at the natural counterpart of the quotient rule for exponents. It is, of course, the quotient rule of logarithms. And it states that the logarithm of a quotient, the logarithm of x divided by y, can be rewritten as a difference of logarithms, as the logarithm of x minus the logarithm of y. Now, this time, instead of doing an example, let's think about why the quotient rule is actually true, because it turns out that it can be easily derived using the power and product rules. Here's the idea. The logarithm, and we'll just go ahead and not specify the base here for convenience, of x over y can of course be written as the logarithm of x times y to the minus 1. That's just a basic property of exponents. Now we can use the product rule for logarithms to write this as the logarithm of x plus the logarithm of y to the minus 1. And this, in turn, using the power rule for logarithms, can be rewritten as the logarithm of x minus the logarithm of y. We've taken that exponent of minus 1 on the y term and moved it out in front to rewrite the logarithm of x over y as the log of x minus the log of y. If you keep these ideas in mind, then you'll actually understand why the quotient rule is true, and you won't have to memorize it blindly. Let's have a look at a more involved example problem. This time, the goal is to take the expression involving logarithms shown on the screen and to simplify or condense it as much as possible using properties of logarithms. And one way to begin this problem is to take a look at the first two additive terms, and then to use the product rule to combine them into one. So by the product rule of logarithms, this will be the natural log of x plus 1 times x minus 1. We simply multiply the inputs of the previous two logarithms together. Next, we can simplify the first term by multiplying the expressions that appear within it. So x plus 1 times x minus 1 is x squared minus 1. And now, taking a look at the second term, what we can do is apply the power rule. We can take that coefficient of 8 in front, and we can move it as a power on the inside. So this will be minus the natural log of x raised to the power 8. And finally, we can combine the two terms shown in our third line using the quotient rule. This difference of logarithms will be the logarithm of the quotient. It'll be the logarithm of x squared minus 1 divided by x to the power 8. And this is a reasonable simplification of our original expression. Here's an important fact related to properties of logarithms. You can use the power rule of logarithms to change the base of any exponential function to any other base that you like. Here's how it works. Suppose that you start with an exponential function of the form a to the x, and you would like to convert the base from a to b. Well, a to the x will of course not equal b to the x exactly, but there is a nice relationship between them. What we can do is rewrite a to the x as b to the power log base b of a to the x. This follows immediately from the fact that b to the x and the logarithm with base b are inverse functions, so when you compose them, you just get the input right back. And now we can simply use the power rule of logarithms to take this exponent inside the logarithm and move it out in front. And when we do that, we can rewrite our expression as b raised to the power of log base b of a times x. And just like that, we have started with an exponential function with base a and converted it to an exponential function whose base is b. You can always do this to convert between any two bases. Let's look at an example. If a slime mold doubles in size every day, then what is its continuous growth rate? To answer this question, let's begin by setting up an exponential model of the slime mold's size. We're going to call that S of t. Since we don't know what the initial size of the slime mold is, we'll just leave that as p. But since we know that it's doubling every day, we'll work with the base 2 and have our variable t measure time in days. To figure out what the continuous growth rate is, what we want to do is convert our function to base e. The initial amount, p, will remain the same, whatever it is, but now we'd like to write this function using the base e. Go ahead and see if you can convert 2 to the t to base e. The answer, which you hopefully arrived at using the change of base formula, is that 2 to the t converts to e to the natural log of 2 times t. And once we see that, we're immediately able to read off the continuous growth rate. The continuous growth rate will simply be the natural log of 2, which works out to be roughly 0.69, or roughly 70%. And this gives us some interesting information. If a quantity doubles every unit of time, then it increases by 100% every unit of time. And we now know that that is the same as having a continuous growth rate of just about 70%. In general, converting to the base e will always give you an exponential function's continuous growth or decay rate. You can simply read it off of the exponent. And we now know the secret. To convert to base e, we have to use the change of base formula and apply a basic property of logarithms.